Hello, Mr. Claudia here. Today we have our final lesson in integral calculus for this grade 11 course. We will of course come back to integration later with some applications, but this is the last sort of thing we're going to look at right now. It's the area between two curves. At this point we've learned all about the definite integral and how integration helps us find area. Now we're going to apply this to finding the area between two curves. So imagine you have a curve. Red pen. Let's just draw one like this, some curve, and we'll call that y1. And let's draw another curve. I'll make the second curve actually just be a line. You can think of it as having an upper curve and a lower curve. And I want to find the area between those two curves from a certain x value, x equals a, to an upper bound or upper limit, x equals b. Well, as long as y and 1 are continuous and y1 is greater than y2, so that is you have an upper, the upper function is upper for the entire duration of the area I'm looking at, then the area can be found as the integral from a to b of y1 minus y2 dx. Now, there's a lot of different ways of writing this. Different textbooks do it different ways. The important thing is that it's always the upper function minus the lower function. So in this lesson in your textbook we define the upper one as y1, the lower one as y2. Some textbooks do it differently. We'll just make a little note here that you can also use, if it makes more sense to you, you can also use y upper minus y lower, or some textbooks use ya minus yb. The important thing is that you're subtracting the top from the bottom. Now note, and we're going to talk about this, I'm going to mention this 100 times, but unlike the definite integral, remember our definite integral lesson? Definite integral can be positive or negative. If you have the area and it's below the x-axis, it's a negative area. That's for a definite integral question. But when we're talking about the area between two curves, it's always positive. So even if this area between the two curves was below the x-axis, it's still a positive area. Think about it. You want to buy a rug that has an area of 5 meters squared. You can't buy a rug that has an area of negative 5 meters squared. So area between two curves is always positive, and that's a big distinction that IB sometimes gets really hung up on. So please make sure you're comfortable with that idea. Now when we're doing integration application questions, I'd like to kind of break down the integral. So let's write this again. The integral from a to b of y1 minus y2 dx. How do I remember this, or what does this really mean? Well, if you remember, the integral, based on those last two lessons, especially that long lesson where we looked at the Riemann sums, the integral basically tells us to add up all of those infinite number of rectangles. So when I see this, it means it tells us to find the sum of infinitely many rectangles from x equals a to x equals b. This sort of strategy that I'm going to go through is useful not just in this course but beyond when you keep studying integration. It's useful to think of the integration operator as definite integral, that is where I have limits at the top and bottom. Think of this as saying, I want you to add up an infinite number of tiny rectangles. So let me draw one of those rectangles here. Doesn't have to be perfect, but again, this helps me visualize what the equation is saying. So you have one of those infinitely small rectangles. Now, I can't draw it infinitely small, I just draw it very small or very narrow. Now, what this part of my equation is this is the height of one rectangle. And this is the width of one rectangle. Remember, if dy dx is like delta y over delta x, then dx is like delta x. So that's kind of my reasoning there. So this means add up all these rectangles, infinite number of rectangles from A to B. This is the height of the rectangle, right? And that's pretty clear from my picture here. The height of this is y1 minus y2. The width is a little more abstract. The width is dx. Dx, remember, dy dx is kind of like delta y dx. So dx is kind of like change in x or delta x. So this width is the change in x or delta x. So that's kind of how I look at this definite integral. Height times width, and then do that an infinite number of times. If you don't like that, that's fine. You can just remember this formula. I believe it's on your formula sheet. Let's try doing this question. We'll find that the setup is really the hardest part. Then we're just doing integration. Find the area between y equals x plus 1, x squared plus 1, and y equals x. Well, let's do a quick sketch. It always helps to do a sketch. It's almost, especially as they get harder, you will have trouble if you don't do a sketch. And we don't want no trouble. So there's y, there's x. Okay, so y equals x squared is x squared plus 1 is the mother parabola plus 1. So it's been, raised, shifted up 1. So let me draw that. I'm not going to label it just yet. And then hopefully you drew a nicer parabola than me. Then the second graph is y equals x squared, y equals x. That's a linear graph that goes through the curve, goes through the origin. So I'm going to draw that. Again, my scale is not great here, but it looks something like this. Maybe I should have used graph paper. Oh well. Okay, so, and now we can see, we're actually adding from x equals 1 to 3. So x equals 1 is somewhere here. Oops. And x equals 3 is somewhere up here. And so this is actually the area it's asking for. Now if I'd used graph paper, it would have been a bit of more obvious drawing, right? Like this goes through 1, 1. This goes through 1, 2, I guess. So anyways, I know it's kind of, just going to take my word for it on the drawing, but if you graphed it to scale, you would get this shape here. So now it's pretty clear to me that this is the upper. So I'm going to label it y1 is x squared plus 1, and this is the lower, y2 is equal to x. And I'm adding from the area from 1 to 3. So now I just have to very carefully write my integral. The bounded area here between these two curves is the integral, let's write out the formula, from a to b, y1 minus y upper minus y lower dx. Okay, let's sub in our values. So that's from 1 to 3. Y1 is x squared plus 1. Subtract y2, which is just subtract x, dx. And now I am right. That's just an integral. Actually, it's just a definite integral. So I'm going to find the definite integral. So x squared, well, that's third x cubed. This becomes x. And this is minus x2, so I have a half in front. So there's my definite integral. And my bounds are 3 and 1. Okay, now if you remember from definite integral, our fundamental theorem of calculus, I just sub in 3. So I end up with a third 3 cubed plus 3 minus half 3 squared. Take away, and I like to put a big bracket here so I don't make a mistake with my negatives. a third 1 cubed plus 1 minus half 1 squared. Now this is no longer a calculus problem, this is just a bedmass problem, really. Make sure you do your exponents first. So I end up with 3 times 3 times 3, which is 27 over 3, plus 3 minus 9 over 2, minus, so just be careful here that you are distributing that negative to each value in the bracket. So I end up with negative a third, negative 1, plus a half. Now this is no longer even a bedmass question, this is just a fractions question. What do I get? 3. This is 9 plus 3 minus 9 over 2 minus a third minus 1 plus a half. Okay, I need a common denominator. Man. Let's do a common denominator of, well, I guess I can collect my terms as well. 9 plus 3 is 12 minus 1 is 11. Negative 9 over 2 plus 1 over 2 is minus 8 over 2 minus 1/3. I guess I can keep doing this. 11 minus 4 minus a third. 7 minus a third. So now I should have a common denominator. This is over 1, so I'm going to multiply. So I have 21 over 3 minus a third. Oh, right, we get 20 over 3. Oh my god, look how much math that is. Sure, but really this was all just easy stuff, like grade 9 stuff. The calculus is up here. And really the only thing that's new for you guys is the fact that we have to make this equation, this integral very carefully. That is our easy example. Let's turn the page and we'll do a more difficult example. Actually, it's a medium example, medium difficulty. Find the area between these two curves. And you might say, why is this medium? It looks almost exactly the same. Well, let's sketch it and we'll find out. So try to do a little bit better of a sketch this time. Okay. Okay, I can sketch this first one, y equals x plus 2. That is a linear equation with a slope of 1, but then I move it up 2. So how about somewhere up here? Promising. Okay, my second equation is, well, it's a quadratic. I don't know how to graph that. Well, to sketch, I do know how to graph it. I have to remember my quadratic skills. To sketch y equals x squared plus x minus 2, we have to convert to factored form. So let me factor that. It's probably factor it by inspection. I have a 2 and a 1. The 2 is more positive, is more powerful, so it gets like that. So therefore, I have a x-intercept at x equals 1 and x equals negative 2, and the parabola opens up. So it's good we spend so much time on parabolas because I have to know how to sketch them quickly. So this line goes through, if x is negative 2, so this is actually the intersection here. But this is one of those those zeros is here. This is negative 2, and the other point is 1, so it goes through here. So it's some sort of parabola. Again, this is just a sketch. Oh, terrible sketch. But it looks something like that. You might be slightly off in your sketch, but the important thing is that you can see now the graph, which graph is on top. This is y1, x plus 2. The line is on top. This is y2, the quadratic, x squared plus x minus 2. And the area between the two, I can clearly see like that. So now we just need to find the area using the formula. So bounded area is equal to the integral from a to b, y1 minus y2 dx. Let me sub this in. So now I need to sub in my bounds. Okay, and now we have a problem. We see why this is a medium example. I don't know what the lower and upper bounds of integration are. I don't know what these x values are. So why is this question harder? Well, we actually have to figure out what this point is and what this point is. And you guys can do that. You did a whole, you've done this before. You need to find the intersection point. So first we need to find the bounds of this area by finding the intersection. Oh, the points of intersection. If you guys remember how to do this, to find the points of intersection, you set y1 is equal to y2. y1 was x plus 2, y2 is x squared plus x minus 2. Now, how do you solve quadratic equation? This is just a quadratic. Well, I have to collect all my like terms. So I'm going to bring these things to the other side. So I end up with x squared, subtract x from both sides, so the x's disappear, and subtract 2 from both sides, so I end up with minus 4. This is a quadratic. How do you solve a quadratic? You factor. Get two answers, x plus 2, x minus 2. So therefore, x equals negative 2 is one of the points of intersection, and x equals 2. So now I know that this is x equals minus 2, and this is x equals positive 2. So now you can start writing out your definite integral. You go from negative 2 to 2, and then we have x plus 2, that's my first function, y1, minus x squared plus x minus 2. Notice how, just to be safe, I'm putting lots of brackets in to make sure. Like, subtract this function, so there's a negative that's going to be distributed. Be very careful you don't mess up a positive or negative. I get now x plus 2 minus x squared minus x plus 2 dx. I can combine my like terms, and I end up with x minus x, so those disappear. So I end up with 2 plus 2, which is 4, minus x squared dx. Now this is just an integral. I can solve this. The integral of 4 is going to be 4x. And for x squared, well, this becomes x cubed, 1 over 3 to get rid of that constant. And those are my bounds. Now I can sub in my bounds using the fundamental theorem lesson we did yesterday. So 4 times 2 minus 1/3, 2 cubed, minus, remember I like to use a big bracket here to make sure I don't make a mistake, 4 times negative 2 minus 1/3 negative 2 to the power of 3, and oh, sorry, there's my big bracket. Now it's just order of operations. Be very careful about your your math work here. 4 times 2 is 8, minus 2 times 2 is 4 times 2 is 8, 8 over 3. So minus minus is going to be plus 8, and minus 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 again is going to be, I mean, if you like, you could, minus minus is plus, but then this is actually negative 8 over 3. So you end up 8 plus 8, which gives you 16, minus 8 over 3, minus another 8 over 3, which is minus 16 over 3. It always ends up being these annoying fractions you have to solve. To get this common denominator, you have 48 over 3 minus 16 over 3. That gives you 32 over 3. So once again, the bounded area is a number, and it's always positive. And we did it by setting up the integral and then doing performing our kind of fundamental theorem of calculus. This question is harder though, because to find the bounds I had to do some intersection work. So that is the lesson for finding the area between two curves. And there's your homework practice. There are 7 questions to do. I've given you the answers. And these are questions you should try to do without your GDC, because as you see, these questions don't require a calculator, and you could have to do them on a paper 1 exam. Now I know what you're thinking. If there's an easy and a medium example, surely there must be a hard example. And there is. Well, is it a hard example? Yes and no. It's a very hard example, but it's a GDC example. So we're going to show you how to do one of these questions with your GDC, because the reality is, yes, you could get a question on a paper 1, but you could get it on a paper 2 as well. And the strategy is a little different. So let's do this GDC example. So this is 3.7 page 3, and this is the GDC example. Okay, so we have, let's scroll up a bit here. We have these two curves. Now, first of all, I know this is a quadratic. This is a cubic function, though. I'm not great at drawing cubic functions. Slash, you might not have learned this last year because of COVID. But I don't need to because I have my GDC for this question. I'm just going to immediately graph those functions. Like, I'm not going to bother even thinking about it. I go onto my graphing calculator, I press tab, and I enter the two functions. So what's the first one? 10x plus x squared minus 3x hat to the power of 3. Press enter. Okay, then press tab again. My second function is x squared minus 2x. Press enter. Okay, now I have two graphs. Okay, so let me zoom out a little bit. Or actually, what I'm going to do is change the zoom to go from what? X negative 5 to x positive 5. And from negative 7, how about I go negative 10 to positive 10? So menu, window zoom, settings. So I'm going to go from negative 7 to positive 7. Is that what I said? I think I said negative 5 actually. Negative 5, positive 5. And let's go negative 10, positive 10 for y. Press enter a few times. Okay, that's a little bit clearer. And now I can see that, what are we trying to do again? We're trying to find the area between these two curves. So you can see that there's actually two areas. There's this area and this area. They're similar in that they're both between the curves. They're different though, because for the left-hand area, this parabola is on top and the cubic is on the bottom, and then it flips. For this area, the cubic's on top, the parabola is on the bottom. So let's do a quick sketch just so that we have this on our page. And if you're doing this at home, you might have to use a graphing software like Desmos to help you out. So I have I'm going to draw this with two different colors. I have this nice cubic function that looks like this. Graph doesn't have to be perfect. The idea is that you're able to understand the shape though. Something like that. That is y is equal to, that's my cubic, so 10x plus x squared minus 3x cubed. And then I have my parabola, which is kind of like this. Again, I'm not the greatest artist. This is definitely not very beautiful, but there I have my my two graphs. And what we found, what we were just talking about, is there's an area here that's A1, and then there's an area, oh, I drew this wrong. Oh, no. Oh, so embarrassing. So, okay, pretend I didn't do that. So now this is all, if I just shade this in, this is area 2. This is a common mistake, is to just treat it as one, but it's two separate areas because the function on top changes. So important. But what we need to do first, okay, so yeah, let's write down here. A is equal to A, oh man, it's lunchtime, so I'm tired. A is equal to A1 plus A2. let me just make a little note here. We need to use two areas because there is a different upper function for each area. So that's the reason why. But no problem, because we have a fancy formula, which is the integral of, okay, we need the lower bound. And the upper, okay, so for a1 I need to know this x value and this x value. Okay, so to find the points of intersection, we have to set y equal to y, so we have to set x squared minus 2x equal to 10x plus x squared minus 3x cubed. And then we have to solve for x. No, wait a second. We don't have to do that because we're in a calculator exam. We're in a GDC exam. So there's no way I'm going to solve a difficult cubic equation like this by myself on my own. I'm going to use my calculator. To find the intersection points, I taught you this a long time ago, you press Menu, Analyze Graph, Intersection. And then I'm going to use the calculator to find the intersection. So remember, it's asking for a region because there's 3 intersection points. So I'm going to go to the left of the first intersection point, click, and then scroll to the right. And then click, give it that region, and we see the first intersection point is -2, 8. See how powerful the graphing calculator is? Menu 6, Analyze Graph, Intersection 4. Same thing, I'm going to give it a bound. Okay, that one is 0, 0. And finally, Menu 6, Intersection, and that is 2, 0. So I'm just going to say that instead of doing this, but it is easier to just use the GDC to find the points of intersection. And those points are -2, 8, 0, 0, and 2, 0. Okay, so now I can build my integrals here. So a1 goes from -2 to 0, and in this case it is, I'm going to call this, I guess we're going to have to call them one or the other. Let's call this YB, and let's call this YA. So I'm going to have for A1, it's going to be the red one, so it's going to be YA subtract YB dx plus integral, so now we go from 0 to 2. In this case it's the black line, so it's YB is the upper minus YA dx. Now let me enter the equations. So I have YA, which is x squared minus 2x. Then take away the black one, which is 10x plus x squared minus 3x cubed dx, plus, from integral from 0 to 2, okay, I have YB, which is the 10x plus x squared minus 3x cubed, minus, and then I open the bracket just to be careful, x squared minus 2x dx. You could enter this as written, but it's probably worth and quicker to just do a little bit of simplification. So this is x squared minus x squared, negative 2x minus, so it's minus 12x plus 3x cubed dx. So I'm just quickly simplifying this a little bit more. If 10x plus 2x, so I end up with 12x. The x squares cancel out. I end up with minus 3x cubed dx. Okay, now, if you didn't have your calculator, you'd have to do a lot of work here, but we do have our calculator. So I'm just going to write dot, dot, dot using GDC. And, oh, now I have to go to my calculator mode. So let's go, oh, tab, there, I mean calculator. Oh, I was doing something before. Let me delete this. Actions, clear history 5. Okay, so now I'm going to just type the integral. So menu, calculus, numerical integral. I have negative 2 to 0. This would be negative 12x plus 3x squared dx plus menu, calculus, numerical integral. Same thing, 0 to 2. I like to use the arrow keys to move around here. 12x minus 3x to the power of 3. Oh, I made a mistake. Look, I gotta go back. This should be a 3, right? Negative 12x plus 3. X to the 3. Okay, and then I go over here. I forgot to put the x here. Press enter into that line of code, and it spits out an answer. 24. All that work, and the answer is 24. So you see how we were able to leverage the calculator to do this question, which would have been a lot of work by hand. There's a few notes I want to make. So one is that you use the calculator to find the points of intersection. You don't do that by hand. You use the calculator to help you find the sketch. You use the calculator to solve the integral. There's an important point here, which is we never show what buttons we've typed into the calculator. That's an important thing. So we always have to write in the correct notation. I'm gonna write that here. Always use math notation. Do not write which calculator buttons you pressed. That's an important thing throughout this course. IB does not want to see what calculator buttons you press. They want to see the math notation, and then just that you're using the GDC. So this is perfectly acceptable. Just put your answer, and you can even put GDC. That's a nice form to tell the marker what you're doing. The other two more things I wanted to tell you. One is that the GDC questions will have less marks for your steps as you go. So for example, this mediums question, you'll get marks along the way because you don't have a GDC. Here, there's different marks awarded because they're not going to give you any marks for doing the integrals yourself. They're expecting you to use the GDC. If you want to pick up a method mark, this is a really good line for a method mark. Just want to make sure I'm saying this right. Worth a method mark. So there's a tendency sometimes with the GDC exam just to write the final answer because you're typing it all into your calculator anyways. That's good, but then if you make any mistakes, you don't get anything. So if you are going to write some method marks, if you do want to write something down for this question, this is a very good line. It's a quick line. It's easy to write. You don't have to do too much, right? You just have to basically say this function subtract this function with the integral sign and some bounds. This is worth a method mark to you. So for a marking scheme for this question, you might get 1 to identify the points of intersection, 1 to identify a few areas, 1 to show me that you understand what you're doing, and then you go right to the final answer. but you might be saying, well, what about this? I had to do this work. Well, last year I found out that there's another function that's really quick for doing this. I think a student showed me. I'm learning on this calculator every year, just like you guys are learning. So if you go back to the calculator mode, I believe what you can do, again, the student found this, you press Menu, Analyze Graph, and you go down to Bounded Area. Now, I think this works. The lower bound, I'm not going to use the scroll because it's not super accurate. I'm just going to type the lower bound, which was from our graph, it was -2. So I'll write -2, press enter. And then it wants the upper bound, which is from our graph is 2. And there we go. And you can actually see the calculator shaded in the area, and there's 24 there. It's hard to see. I hate the text. Sometimes you have to move it. But it did figure out, if I press Control Hand, I can drag that answer. There's 24. I'll drag it over here. So it does figure out the bounded area. So that is a kind of a shortcut. I like showing the work and going through it methodically, but you could see once you've graphed it, found the points of intersection, you can go from here, basically from here, even without any of this, you could go right to your answer. Again, this is why it's very valuable to write out this line. At the very least, if you write out this line, it saves you. If you type anything wrong into your calculator, you would get nothing, but at least you'll get some method marks and some intersection point marks. So please, if you're going to be brief with your GDC solution, especially if you're going to use that bounded area, please make sure you write something like this. So let's just make a little note of that. The bounded area can be found even easier in graphing mode by using, what is that, Menu 6, Analyze Graph, the 7, bounded area. And I'll just say type the upper and lower bounds. So that is our lesson on finding the area between two curves. You've seen how to do it with the calculator, and you've seen how to do it without the calculator. Your homework, the previous page I gave you homework without the calculator. This homework is with the calculator. So page 317, number 1 to 5, and that is GDC required. You can't do it without. Hopefully you have your calculator access to it. If not, you can use Wolfram Alpha or Desmos. Have I talked about those yet? You could, if you don't have a GDC with you, you could use Desmos.com, but that's only graphing, so it doesn't give you too many options for solving integrals. Wolfram Alpha, wolframalpha.com, that is very powerful graphing calculator. So good luck, substitute for your GDC. So good luck with that, and we will see you next time.